So today I'm going to begin picking up where we left last week. We were doing an FM broadcast flow graph to listen to FM radio stations. So the same thing we were doing in GQRX, but using a radio companion. And then I will go on to the next tutorial, which is about spectral analysis. That is this folder here, which has really two parts to it. The first part is about how to generate different types of signals in GNU radio, and the second part is how to use a spectrum display or an FFT to analyze those signals. So that is probably very, very useful for those of you who are doing any kind of RFI analysis, because oftentimes when you have RFI, the first thing you begin with is by doing some FFTs, making some spectrum captures, and getting some notion of how the RFI looks like. So without any delay, let's go into the FM demodulation flow graph. This is what we had last week. As a reminder, the RTL-SDR source is sampling IQ samples. The FM radio station we want to listen to is 300 kilohertz above the center frequency, which is 98.5 megahertz. And so we use this multiply with a cosine of frequency minus 300 kilohertz to move the signal to DC, to 0 hertz, to the center of the screen, if you will. And then we use this low pass filter to eliminate all the other stations and the noise. So let's run this again. So we have the station we want to listen to here at 300 kilohertz. And then this is in red, the output of the multiply block. So the station is in the center, and this is the shape of the low pass filter. All the other stations and all the other noise has been removed. The next thing we want to do is to reduce the sample rate, because last week we were seeing that there is something called Nyquist's theorem, which relates the maximum signal bandwidth you can represent with the sampling rate you use. And for a complex signal, here everything is complex. That's what the blue connections stand for. Nyquist's theorem tells us that the bandwidth we can represent is equal to the sample rate. So here we have the FM radio station. The bandwidth is slightly less than 300 kilohertz, maybe let's say 200 kilohertz or so, albeit we are using 3.2 megasamples per second. So at this point, when we have low pass filtered and remove all the other signals, we can decimate, which means throwing away keeping one out of every 10 samples or 20 samples or 15 samples or whatever, so as to reduce the data rate and so as to reduce the number of computations that the CPU needs to do. So that's the thing we will be doing. But before that, small comment. So here we have the signal source and the frequency is minus 300 kilohertz because the signal we want to tune to is 300 kilohertz. And if we want to move that to the center to 0, then 300 plus minus 300 is equal to 0. However, this can be quite confusing. For example, if I want to put here an entry so that we can select the FM radio station we tune to. So I can call this tune frequency. This is in hertz, for example, and then this is going to be a float. I really want this to be 300 kilohertz because otherwise it's going to be quite confusing. What I want this to work is the user can see there is a station here at 300 and then they can enter 300 here. And if they want to go to this one, then it's, I don't know, minus 1 megahertz. So they could go here and enter minus 1 megahertz. So of course I can do minus tune frequency here that would get me where I want, but I also want to show a different way to do it, and the different way to do it is rather than using a multiplication, we use this multiply conjugate. So multiply conjugate is this input times the complex conjugate of this input. In comparison to multiply, which is, let's say this is A and this is B, so this is A times B. And in this case, if this is A and this is B, this is A times B conjugate or B bar or whatever. So what happens is when we hook the complex exponential here and we compute the complex conjugate essentially changes I by minus I or J by minus J, however, whichever notation you want to use. So here a complex exponential has the frequency on the exponent. So this is something like exponential of I times 300 kilohertz times the time variable. So taking the complex conjugate is really the same as flipping the sign of the frequency. And what this allows me is to use a multiply conjugate here, and then I can have the positive frequency here. So oftentimes it's less confusing to do it in this way. Just you need to remember multiply conjugate instead of adding frequencies is subtracting frequencies. So this frequency minus this frequency because of the complex conjugate. So tune frequency, okay. And then we can check that it works as expected. So yeah, 300, this is the station at 300. If I want to go to the station at 1 megahertz, I can enter here 1E6, for example, which will appear like 1 megahertz. And yeah, something hasn't worked. No, I want to go to this one, which is minus 1 megahertz. Accidentally, I have gone to here, which is plus 1 megahertz. So minus 1 megahertz is minus 1E6, and now we can see that the shape of this signal is the same as the shape of this signal. So that's what I wanted to show. Any questions here? Okay, so we want to decimate, and let me check what I used on the final flow graph. Yeah, decimation by 10. So yeah, the reasoning here is coming back to the spectrum. We have 3.2 megahertz of bandwidth. If we decimate by 10, the bandwidth is reduced to 320 kilohertz. That's just 1/10 of 3.2 megahertz. But then 320 kilohertz is more than enough to fit the signal inside, because that will give us from minus 160 to plus 160, so from here to here. And last week we were using this keep one in n, so I could go here and say keep one in n, I want to keep one sample in every 10. But we can do this in a better way, because what happens is this low pass filter is computing all the samples, and then we are throwing away most of the samples. We are only keeping one sample in every 10, and the other 9 are being thrown away. So rather than just discarding those samples, it's better not to compute them in the first place. So that's the reason this low pass filter has a decimation. We can put here 10. And then what happens is this low pass filter knows that it only needs to compute one output in every 10 output samples, so to speak. So no computations are done in vain. Decimation 10, I'm going to put that in a variable because that might come in handy. So decimation. And at this point, one might be tempted to go and press run, and this will not work. So it freezes just immediately. And the reason is often in GNU radio, when you have a block which has several inputs, especially one of these display blocks, so the frequency sink and the time sink as well, that block expects the rate of the two inputs to be the same. It also happens with many of the mathematics blocks. So for example, this multiply conjugate expects the rate of these two inputs to be the same. If you supply inputs which are at different rates, then things freeze, because basically what happens is by doing the connections like so, in here we have 10 times more samples than in here because of the decimation by 10. So more data is arriving here, and when trying to put together some 4096 points from input 0 and some 4096 points from input 1, basically things do not work as they should, and all the flow graph freezes. The solution to this problem is quite simple. We just use two of these blocks, each of them with one input, and then we can have completely independent sample rates in each of the blocks. And something we need to remind ourselves is to adjust the bandwidth anytime we are using decimation. So here bandwidth 320 kilohertz. And now this will work. But I should also change this label. So this is the same thing as before. The radio station at 300 kilohertz is being moved to the center to 0, but then we are also only taking the central 1/10 of the bandwidth or of the spectrum. So this is what we see. And if I do something like auto scale, then we can clearly see the shape of the filter. So let me change this label and continue doing things. So this is the, let's say, the low pass filter spectrum, something like that. Okay, at this point we have our signal. We have eliminated all the other signals that are received by the SDR. And now we want to do something with the signal, and this is an FM signal. FM means frequency modulation. When we want to transmit any kind of data, it might be analog data, as in this case, or it might be digital data. We do so by changing at least one of the properties of a radio frequency wave. The properties we can play with are the frequency, the amplitude, and the phase, basically. There are other quantities that can also be changed or modulated, such as the polarization, but that's not so common. So the most three common ways of modifying a signal to send some information are frequency modulation, amplitude modulation, and phase modulation, which just means that we are changing one of those quantities to convey the information we want to transmit. So in this case, frequency modulation, that means that the frequency of the signal is changing as the voice of the music is changing. That is also an analog wave, albeit it's an audio frequency wave. So that's what causes the spectrum of the signal to be spread in frequency rather than concentrated at a single frequency. This is because the frequency is changing so fast, we can imagine that it's constantly sweeping across this region. So how to process that in GNU radio? There is something which is called Quadratic demodulator that obtains the instantaneous frequency of a signal. So in here you put a complex signal, and the output is going to be the instantaneous frequency. And there is some gain, which I will explain in a moment how it works. So to look at this, we can use a time sink and maybe also a frequency sink. I'm using the shortcut of pressing down arrow when this block is selected, but we can also change here as a float complex. Remember, these input-output types need to match. So these, and then frequency sync as well. Whoops. You can also rotate blocks, by the way. So there is rotate counterclockwise, rotate clockwise. If you do very complicated flow graphs, that might be a way to keep them more tidy. So 4096 here, and I think I'm good to go. Yes, I also need to divide these two by decimation. So this is the time display. And we can see there is something changing. It's not clear how to interpret this information. We can also see the spectrum here, and it's symmetric because this is a real signal, and I have forgotten to use the half option here, so maybe that's more useful. Let's run this with half. So maybe I can put some averaging here, and we see a few things. Let me zoom into this piece of the spectrum, which is the most important one. Here we see some range of frequencies, which is between 0 kilohertz and 15 kilohertz, more or less. And this appears to be changing. This is the FM audio, the audio on the station. So if there's music, this is the music. If there's voice, this is the voice. And this is the thing we want to eventually drive to the computer speakers so that we can listen to the station. But there are also other signals here. And the interesting part about FM radio stations is that many of them do not just transmit a single piece of information, but multiple in a way that they are combined by using something which is called subcarriers. So if you think about an FM radio station, what kind of signals could you want to transmit? And yes, there is the audio, but we oftentimes have stereo audio. So that's a left channel and a right channel, and that's really two audio channels. The way that stereo is done in an FM broadcast station is not by transmitting the left channel and also the right channel, because some FM receivers, particularly very old FM receivers, are mono, so they do not support stereo. They just have one audio channel. So the way this is done is in here, there is the mono information. So this is the sum of the left and right channels. And if you have a receiver which is mono, then it will only use this part of the signal, and you will get left plus right, which is basically the best thing you can do with just a single audio output. And this is what we are going to be doing today. But there is also the signal here of left minus right. This is the stereo information. It's the difference between left and right channels. And if you have this left plus right and left minus right, you can add them up to have the left channel, and you can subtract them to obtain the right channel. And that's how a stereo receiver works. But then something to notice is the range of frequencies here comes from 0 kilohertz to 15 kilohertz, or more or less. These are audio frequencies. These are frequencies we can directly listen to. It's the human hearing range. But in here, everything is around 38 kilohertz. And the reason is we cannot transmit more data here because we can only put one single channel of information in this frequency range. If we want to transmit another stream of data, we need to move it in frequency and place it somewhere else. So what happens is the audio for the stereo channel for left minus right is shifted in frequency by 38 kilohertz. We already know how to do that by multiplying with complex exponential or with cosine function, and then including a filter if necessary. So basically you can imagine that this is more or less the same kind of information as this, but the 0 has been moved to 38. And then this is symmetric because we have a real signal. We have shifted it up in frequency, but still we have this symmetric spectrum of real signals. This is just like last week. So this is left minus right. And we also have these two things. What are they? When you have a receiver and you want to process this signal, you need to move this again down by 38 kilohertz. So you need to subtract 38 kilohertz. And if there is a frequency error, even if it's small, between the transmitter and the receiver, this will sound very bad because you are shifting, let's say, not by exactly 38 kilohertz, but by 38.001. Let's say you make an error of 1 hertz. So then you are shifting all the frequencies by 1 hertz. And yes, that's something you can notice. And it shouldn't be done in that way. So the way to do it properly is to transmit what is called pilot tone. This is just a CW carrier. It's a pure tone. There is no modulation here. This is a sinusoid at a frequency of 19 kilohertz, and 19 is the is 1/2 of 38. So what happens is the receiver will look at the frequency of this signal and then multiply by 2 to obtain the 38 kilohertz value or reference that is used to shift the stereo information back to 0 hertz. And by doing so, the receiver makes sure to use exactly the same value that the transmitter used, because everything comes from this 19 kilohertz tone transmitted by the transmitter. So that's what this 19 kilohertz tone is. And then what is here, this is something at 57 kilohertz, I think. And that's supposed to be 3 times this pilot carrier. That's no coincidence. Again, it is a way for the receiver to be able to tune to this signal with a very precise frequency. And the information here, we can see that the shape is more or less the same always. It's not going up and down as would be voice or music. And this is because this is digital information. This is called RDS, which is radio, I don't know, I forgot, but it's when you have a fancy FM receiver which has a screen, so for example in your car, and it displays the name of the station you are tuned to, and it might also display the name of the song or the name of the program, that comes from the digital information here. So that's what it is. Okay, so we have all of these signals. They are all combined in the frequency modulated signal, and we want to extract only this part because this is the mono audio from the station. Any questions here?
The L-R bump at 38 kilohertz keeps going away sometimes. Is that just because the signal is being transmitted as mono only, or does it go away for some other reason?
That might be the case. So this is a classical music radio station, and when they are transmitting music, they probably do so from a stereo recording. But if it's the speaker talking, like presenting the piece of music or whatever, that's a single microphone on the studio. So I've never looked into how they do it, but they might do it as a mono signal.
Makes sense, thank you.
Okay, any other questions? Great. So we need to select this part of the frequency range. We can do that with a low-pass filter. And then something else we need to take care of is the sample rate here is 320 kilohertz, as we can see in all these places. But if we want to send this signal to the computer sound card, we need to use a sampling rate which the sound card can use. And this is typically 48 kilohertz or 44.1. So The best way to figure that out is if you go here and say audio sync. Remember that sync means there is an input but no output. So if you want the speaker rather than the microphone, it is the audio sync. And then there is a drop-down menu of usual sample rates, and 320 is none of those. But we have 48 kilohertz, so we will do 48 kilohertz. And the rest is just putting here a low-pass filter and some decimation or some sample rate change, which we will discuss in a minute by how much we need to decimate to convert from 320 to 48. But before going on to that, let's talk about the gain here. So the gain, I'm not sure if, yes, there is some documentation here which is supposed to be in LaTeX and it isn't rendered, but there are the formulas here on the wiki page. And there is the description of the gain. The simple way to explain this is basically this formula. I'm going to zoom in. So the way that this quadrature demodulator block works is by taking one sample, multiplying it by the complex conjugate. Here the bar means complex conjugate of the previous sample. And then this is a complex number, and it's taking the argument or the angle of the complex number. And how does this work? Well, the angle of a complex number is the phase of the complex number. And if you remember about multiplication of complex numbers in polar representation, then you might remember that when you multiply some number times the complex conjugate of another, you're subtracting the phases. So if we do this in polar representation, the phase or the argument of the multiplication will be the difference of the phases of these two. And the instantaneous frequency is how much the phase changes versus time. So here, this is how much the phase has changed between time n and time n minus 1. Remember that this is discrete sampling. So time is an integer. It just counts samples. The units here are radians because the phase is in radians by sample or per sample because the time step we do is just one sample because of this minus 1. So that's what it means when we have here on the plot. So for example, if we stop and we say, okay, this is 0.35, that means the frequency of the signal at this moment is 0.35 radians per sample. Oftentimes, we do not use radians per sample, we use hertz. If we want to convert, we need to divide by 2 pi. We can get pi from NumPy. I will import the package in a second. And then this would be, if I do it like so, this would be cycles per sample, but hertz is not cycles per sample, but rather cycles per second. And we have some rate samples in a second. So this is the conversion. This gain is the number that is multiplied here by the argument. Somewhere it must be, maybe not, I don't know. At least here, gain setting to adjust the output amplitude. So the gain is multiplied by the argument. And then, yes, I need to import NumPy. So if I do this, yes, the scale of the plot will not be the appropriate, but we can change it like so. And then we can see by how much the frequency of the signal is changing. which is about maybe 500 kilohertz or something like that, somewhat less, so 200 kilohertz or whatever. That is called the deviation. So if you ever hear this concept of deviation when talking about a frequency modulated signal, is by how much the frequency is being shifted. Anyhow, I'm going to, oh yeah, I see before doing this again, I've done a mistake. I was wondering, that seems too large of an output when we are seeing that, and the reason is the sample rate here is not the sample rate, which is 3.2 megahertz, but rather 320 kilohertz. So one needs to be very careful and double check, because here sample rate is sample rate divided by decimation. And then I should get something more reasonable. So for example, here, 65 kilohertz, if I'm reading the scientific notation correctly. This depends on the volume of whatever is being played. So if you have louder voice or music, the frequency deviation will be larger. And if you have some signal which is quieter, then the deviation will be smaller. Because basically frequency modulation encodes the loudness of speech or music or any audio by how much the frequency of the signal is changed. So, okay, I want to revert this to 1 because I'm going to use this output as an audio signal. +1 and -1 is the maximum range of the audio sync, so that will be maximum volume on the speakers. And in fact, I don't want to make this too loud, so maybe I want to have an entry. I'm going to put a multiply constant block here and put here audio gain and audio gain here. And in this way, I basically have a way to control the output audio. So now let's see how we can convert the sample rate from 320 to 48 kilohertz, which is what we need here. And we can check this calculation, and it turns out that the ratio is 6.666. So that means we cannot do a decimation like here by an integer number, because, for example, if we decimate by 6, we obtain 53 kilohertz, which is too much. And if we decimate by 7, we obtain 45 kilohertz, which is too little. We want exactly 48. So how to do that? There is something which is called the rational resampler. And it is called rational because, let me put float, and real everywhere. It's called rational because it works in terms of a fraction or a rational number. So rather than having a single number for decimation, we have a number for decimation and a number for interpolation. And then what happens is that the total rate change is interpolation divided by decimation. So we can basically put 48 here and 320 there. It would be nicer to put this as a fraction in lowest terms. So if we want to do that, we can Wolfram alpha or any calculator and do 48 divided by 320. That's 3 divided by 20. So here we could have put 3 divided by 20. It's the same. But what happens, regardless of what we put, is the sample rate at the output will be the input sample rate, so 320 kilohertz multiplied by 3 and divided by 20. This has a taps parameter, and taps means the filter coefficient. So whenever we have a filter, there are some taps or some filter coefficients. If we search for taps, you can see, for example, we have low pass filter taps. And this block is very similar to the low pass filter, but it doesn't have an input or an output because it only calculates the taps. So we could put anything here, for example, this, and then give this a short name, and we could use filter taps here. And if we mouse over, we can see these filter taps has been computed as a vector of 771 numbers, and some of the numbers are the ones that appear there. But something very nice about this block is that if we leave the tabs empty like this is 2 square brackets, so this is an empty Python list, then this will compute the filter automatically for us in such a way that there is no aliasing. Because the previous week we mentioned that whenever we want to change the sample rate, whenever we want to reduce the sample rate, since we are reducing the amount of spectrum we can represent because of Nyquist theorem, we need to have some filtering, because otherwise the signals which happen at a frequency that can no longer be represented will alias back, so they will wrap around the edges of the spectrum, and they might fall on top of signals we are interested in. So anytime you are decimating, you need to include a low-pass filter or a filter of some sort to avoid this aliasing. And in this case, a rational resampler can compute an appropriate low-pass filter for us if we leave this empty. So what I'm going to do is to include a time sink here, put here 48 kilohertz, and then maybe put some titles, so audio signal, for example. And I think we are good to go because we have the frequency modulated signal here. We are isolating it. Then we are measuring the frequency of the signal, and that gives us multiple real signals. One of those is the mono audio, which already sits at baseband. Baseband is another name for something which is at 0 hertz. And then we can, it's already in the audible range, so we don't need to shift it in frequency. We can use the rational resampler to change the sample rate to 40 kilohertz, multiply by a constant to control the audio volume, and send that directly to the sound card. So let's see if this works. And it works. I can make this louder. And then if the Zoom audio sharing has worked, you can listen to some music which is being transmitted right now. So this is the same as GQRX. You can see the audio signal here, and this will depend on whatever is being played. I was looking with curiosity because if I stop it, you can see this. It is like somewhat wavy, and this might be because some of these 19 kilohertz tone might be leaking in. In fact, we can make sure. So what we can do is add a frequency sink here as well to make sure, because 19 kilohertz is not something that I can hear definitely, but maybe we are sending that to the speakers as well, and we shouldn't really do that. So 48 kilohertz. Yeah, so this is the audio signal spectrum, and we can see here is the music. And here is the 19 kilohertz tone, which is still present because in 48 kilohertz we can go up to 24 kilohertz. It's 1/2 of 48. And you can see the roll-off of the filter here used by the rational resampler, but 19 kilohertz is below that. So how to get rid of this 19 kilohertz tone? Very, very simple. We could use the tabs here to do it in the same step, or we can do it in 2 steps. So we can insert another low-pass filter here. And then the cutoff frequency can be, well, 18 kilohertz, really. If I just want to get rid of something at 19 kilohertz, I can make it 18 kilohertz and a transition width of 500, for example, and that already places 19 kilohertz in the stop band, and here the sample rate is 48 kilohertz. So using this filter, now the 19 kilohertz tone has been greatly attenuated. It's on the same level as the noise here. And the audio signal looks smoother because it only has low frequency content. So this is basically how GQRX works. GQRX is doing all of this using GNU Radio. It's a C++ application, so it has some GNU Radio blocks written in C++ to do all of this. But in here, using GNU Radio Companion, we can put all of these blocks together to achieve the same effect. And the great thing about GNU Radio Companion is that we can see how everything works, and we can experiment with it if we want to see what happens if we change these filter parameters. It's very easy to change. So now I'm going to work with this spectral analysis folder. I have already prepared a blank flow graph, sample rate 1 megahertz. Any sample rate will really work, but 1 megahertz makes the math easier to work with. And then what I want to begin with is how to generate different kinds of signals in GNU Radio. So far, we have used the signal source to generate a complex exponential like this, and we have seen that. Let me put a throttle block here and frequency sync. We have seen that this is a pure tone, so it only has power at a single frequency. It can be called pure tone, CW carrier, or just carrier. So this is a Dirac delta on the spectrum, spike like this. There are other basic signals that often we need to generate. And the most basic of them is noise, white noise. And what do I mean by white noise? Let me demonstrate that by putting here a noise source and then seeing how this looks like. So we have something which is random, and the noise power is the same on all the frequencies. It's flat across all the frequency spectrum. So this is called white noise, and white means that it doesn't depend on frequency. It's the same power on all frequencies. And it's also called additive white Gaussian noise. And Gaussian is because the distribution of the noise is a Gaussian variable. That's the most common type of noise because Gaussian variables appear everywhere in statistics. So this is just another example of how present Gaussian variables are in everything. And it is called additive because it adds to whatever signal we are dealing with. So we were using the RTL-SDR before, and we were receiving some FM stations, but there was also the noise floor, which comes from the electronics of the RTL-SDR and from many other sources, electronics on my house, generating noise, even the galaxy and the sun. So the noise from all those sources can be well approximated as a Gaussian random variable. And this is what this noise source is used for. It has a parameter, which is the amplitude. And let me demonstrate how that works in a second. So noise amplitude. Let's give it a default value of 1 and make this float. And here noise amplitude. And I also want to turn up some averaging. So this is how things look like with an amplitude of 1. The noise level is at minus 44 dBs, more or less. And this really depends on FFT normalization. So minus 44 is not really important here. What is important is if I multiply the noise amplitude by 10, then I get minus 24. So that's an increase in 20 decibels. If I do 0.1, then I have minus 64. So from minus 44 to minus 64, it's a decrease in 20 decibels. The thing you need to remember is a change by 10. So multiplying by 10 or dividing by 10, the amplitude means that the power in dBs grows by 20 dBs or decreases by 20 dBs. And the reason is because power is amplitude squared, or it's proportional to the amplitude squared. So that's the reason we have this 20 dB change rather than 10 dB change. Also, something to mention is maybe it's worth looking at this in the time domain just for a single time. And this looks very random, as you would expect. So every complex sample here is two independent random variables, which are distributed like a Gaussian. And then the amplitude here controls the standard deviation of that Gaussian. But the formula is actually not directly amplitude equals the standard deviation, but rather the standard deviation is amplitude divided by the square root of 2. So in here we have amplitude 1, then the standard deviation of this would be 1 divided by the square root of 2. And the reason is because the power, since this is complex, the power is the real part squared plus the imaginary part squared. And then each of those had amplitude divided by the square root of 2. So when we square those up, we get amplitude squared divided by 2. And we have real and imaginary parts, so amplitude squared. That's the reason we are dividing by square root of 2. To have the power equal to the amplitude squared, even though this is a complex output. Because we can also have real noise. Of course, there is nothing against that. And in this case, the amplitude will be equal to the standard deviation because this is a convention in GNU radio, but it's a helpful convention to avoid making mistakes. Amplitude is related to power as power equals amplitude squared, regardless of whether you have something which is real or complex. So yeah, that's what it is, the noise source. Any questions about generating noise? Okay, now we want to put these two signals together. So to put them together, what I'm going to do is to put here an add block. And then something I want you to notice is that the amplitude for these two signals is 1 for both of them. So they should have the same power. In fact, as we have seen, this is a Gaussian, and the standard deviation of real and imaginary part 1 divided by square root of 2. This is a complex exponential, and the amplitude is 1, so it will have a cosine and a sine of amplitude 1, and the sum of cosine squared plus sine squared is always equal to 1, so the power of this is also 1. And we can see in the time domain, there is this sinusoid of amplitude 1, and then on top of that, there is the random noise because we are adding. However, if we look at the frequency domain here, it is not at all clear that the power of the two signals is the same. In here, we could more or less see, because yes, the power of the sinusoid is related to the amplitude, and then maybe the power of the random variable is more or less the same. It's difficult to tell because it's difficult to see exactly what is the standard deviation just by seeing all this noise, but you can see that they are more or less the same order of magnitude. Whereas in here we have the noise at minus 44 as before, and the CW tone is at minus 8.8. So it's not at all clear that they have the same power. And the reason for that is that to measure power on a spectrum, you need to sum the frequency beams that correspond to the signal that you want to measure the power of. One way of thinking about the spectrum is that it divides the signal into buckets of different frequencies, and then the power of the signal at each particular frequency goes onto each one of the buckets. And in here, the number of buckets is the number of points on the FFT. So the FFT size, we could even put some markers to make this clearer. So these are all the buckets I was mentioning. And when we say that the noise floor is minus 44 or minus 45, what we mean is that the fraction of noise that goes into one bucket has minus 44 dBs of power. But what happens is the noise we have, which has power 1, gets divided over 4,096 buckets because the noise is wide. It has the same power in all the frequencies. Whereas the power for the CW signal, the power for this tone, is only distributed in ideally one of the buckets, but since the signal is not exactly in one of the buckets, some power goes to neighboring buckets, basically. The frequency, I didn't change it, so it's 1 kilohertz. Something which is of interest to compute here is what is the bandwidth of each of the buckets, because we have 1 megahertz of total bandwidth, but then we have 4,096 buckets, so we can have Python, and then 4,096, 1 megahertz divided by 4,096, so each bucket represents 244 hertz of spectrum. And now let's see if that makes sense, because let's say that the signal is at minus 9 dBs and the noise is at minus 44. It's going to be approximate, so plus minus 1 dB, but I just care about the order of magnitude. So of minus 44 minus 9, there is a difference of 33 dBs between the noise and the signal. And then can we explain that by using these 244 hertz, maybe? Because, well, really another way of looking at that is that the power of all the noise. So the noise is present. Where's my plot? Here. The noise is present over all the bandwidth. So the power of the noise, which is in one of these 4096 buckets, is just 1 divided by 4096. And if I want to compute that in decibels, then the formula for computing decibels of something which is power is 10 times the logarithm base 10 of power. And I need to import NumPy. So this is minus 36, which is close enough to the minus 35 that I have eyeballed here from the plot. And this is the reason why the CW signal appears to be 35 dBs above the noise floor. Usually when we are measuring the power of a signal and when we are comparing signals, if we have something which is distributed over several frequency bands, then the total power depends on the number of frequency bands we have in total. So it depends on the sample rate, it depends on the number of frequency bands, basically it depends on all these calculations here. So usually we study a quantity which is independent of the number of frequency bands and independent of the sample rate, which is called N0. It is called spectral density of noise, and it is the noise power in 1 Hertz of bandwidth. Why 1 Hertz? Because we measure bandwidth in Hertz. So if I tell you how much noise power we have in 1 Hertz, then if you want to change that and scale it up to 1 megahertz or 244 hertz, which is the FFT bandwidth here, or any other value, is as simple as multiplying times the bandwidth. So noise in 1 Hertz, that's N0. Let's compute that here. Let's call it N0, put a comment, N0, noise spectral density equals noise power in 1 Hertz bandwidth. So how much should N0 be? The total noise power is noise amplitude squared. This I have already mentioned. And then this is all the power over 1 megahertz of frequency. So the power in 1 hertz is this divided by 1 megahertz, which is the sample rate. So we get basically 1 to the power minus 6, 10 to the power minus 6, which makes sense because this is 10 to the power 6. This is N0, and then we usually set the amplitude or the power of signals we want to study. We set it or we measure it, depending on whether we are measuring something or we are simulating something, in terms of some quantity which is called CN0, and that means carrier power, and carrier is just another name for signal. So signal power versus or with respect to N0. So with respect to the noise power in 1 Hertz bandwidth. Let's add an entry for that. And then I'm going to call this tone CN0, float 60. This is going to be in dBs. In communications, we usually work with dBs because we are often dealing with signals of very different orders of magnitude. So having a logarithmic scale, which is really what dBs are, is very useful to avoid dealing with powers of 10 and such. So 60 decibels, for example, and it will become clear in a moment why I have chosen 60 dBs. And then I'm going to put a variable here to compute the noise amplitude. The tone amplitude. So I'm going to assign it. And how should we calculate this? The first thing we need to do is to convert from dBs to units of linear power. So this is to convert from dBs to something which is linear. You do 10 to the power whatever in dBs divided by 10. This is basically undoing 10 logarithm 10 of linear units of power. So this is 1 million basically. Does this work? Yeah, this is 1 million because 60 divided by 10 is 6. And then this is the tone power, but it is with respect to N0. So if I want to get the absolute tone power, I need to multiply by N0. So maybe some comment here. So Cn0 equals signal power divided by N0. And then this formula makes more sense because if we want to obtain the signal power, we first take care of the fact that this is in dBs, and then this was signal power divided by N0, so we multiply by N0 to obtain signal power. This is the power. We want the amplitude. Power is amplitude squared, so square root of all of these. And I need to import NumPy. You might see some other formulas for this expression which are equivalent. So for example, if you divide by 20 instead of dividing by 10, then you do not need the square root for this factor, but you still need the square root for the N0 factor. So basically we're at the same place where we started because I have chosen the 60 dBs so as to give amplitude 1 for the signal source, which is the same we had before. But now we can change it as we want. And if we make it 50, for example, then the signal drops by 10. So this is at minus 19. You can remember that it was at minus 9 before. We can make it 40. We can make it 30. And we can play a game of what is the weakest signal that we can detect with these parameters. And at 30, it is this tiny tone, which is barely detectable. And as you can imagine, these can be quite important because if you are trying to detect a signal that is weak, then having some idea of what is the signal power or signal Cn0 that your system or your algorithm can detect can be something very important. So in this way, just by changing numbers, we can see the sensitivity of all of these. And we will see how this can improve either later today or next week by doing an improved FFT version of all of these, which is also using an FFT, but not in the best way possible. So for example, to give a clue about how that looks like, something we might attempt is to increase the averaging with the hopes that since everything is jumping around, maybe we are lucky and can see the tone. And yes, sometimes I think it pops up. It should be that small thing here, but sometimes it disappears. It depends on luck, really, because this is random. Questions about this?
Go ahead. Oh, I have a short question. Is there a way to reduce the amount of lag that it does? Because for some reason, whenever I run the flow graph, it severely lags out my computer, and it's only when the time sync is plugged in.
On everything or just on the frequency sync?
The time, the above one.
Oh, that's
Yeah,
strange.
yeah.
Yeah, because for example, you can see that in my computer is instantaneous.
Mine
The
is very
reason,
much so not.
yeah, the reason I was asking if it was about the frequency sync is because depending on the averaging you have here, then you can see that it takes a while for it to react, basically because it has averages of what came before. But yeah, this one should be instantaneous. Which operating system are you running on?
Mac OS.
Mac OS, Apple Silicon or Intel Silicon? Intel
Intel.
Silicon. That's strange. Definitely it's a bug. It shouldn't be like this. I will try to figure out if someone has observed something like this. It might be something about CPU usage. So maybe making the number of points smaller would help, or I don't know. Yeah. Weird bug. Never heard about it.
Okay, so maybe my computer's just been frozen for the past like 10 minutes after I ran it.
That might be it.
I wonder, I mean, if you change the sample rate in the throttle block, does that
I can't.
get, well, your computer's frozen.
Yeah. Yeah.
I mean, I could make it
Speeds
like
up those then.
32,000 instead of 1,000,000.
No, that's also a good point. If you are using sample rate 1 million, as in here, it should be fine because it's not high enough that it would that any reasonable computer would struggle with it unless something is broken or there is a bug. If you put a sample rate which is very low, and I can show that right away, then you might get something like this. So you can see it takes a while for it to update, and the reason is well, it needs 4096 samples, but I'm only producing 1000 samples per second, so at least I need to wait 4 seconds. But then things might work in larger batches, so maybe I need to wait for, I don't know, 10 seconds, 20 seconds, and here I can expect that things are slow. So that's one potential reason. But if you have this set to 1 million, then I guess it's a bug.
Curious as well, if you try a different GUI, whether you get the same issue.
What do you mean a different group?
Rather, because there's other options rather than the Qt GUI.
Yeah, there used to be the WX whatever GUI, but is it available still? No. No, there was another family of GUI widgets which used a different GUI toolkit, but these were deprecated a few years back. I think they were no longer maintained, and Qt GUI is definitely better.
Yeah, might be a bug. All I know is it's definitely the time sync because I just disabled it and it's fine now.
Yeah, that's inconvenient. But anyhow, I'll have a look at the issues on GNU Radio on GitHub. So this is of interest for everyone. So if you go to GNU Radio on GitHub, you have issues, and there are 423 issues open. Some of these are just questions about I don't know how to do something, or feature requests, but others are real bugs, and you can try to search if your bug is in here, and if not, you can open a new issue. And yes, in this case, it should be fairly simple for someone who has an Intel macOS machine to debug it, because it is easy to reproduce. Okay, let's move on. So we know how to generate something which is Gaussian noise, which has a spectrum which is flat, so it occupies all the frequency spectrum. And we know how to generate something which is a signal source, which is concentrated in a single frequency. How about generating something that basically occupies a block of frequencies, something like this, that looks like a rectangle on the frequency plot? So there are multiple ways of doing that, basically because there are multiple types of signals whose spectrum looks like this. But a simple way of doing it is to use again the Gaussian noise source. But then if we connect it directly, we have the same as before, so it will occupy all the spectrum. How can we make this occupy only a fraction of the spectrum? This uses again concepts we have been using since last week, which is the Nyquist theorem and sample rate changes. So this noise source is generated at some sample rate, whatever, and then it will occupy all the frequency spectrum at that particular sample rate. Then if I change the sample rate, the noise will still occupy the same frequency range, but the total frequency range has changed. For example, let's say I generate this noise at a sample rate of 100 kilohertz, which is 1/10 of the sample rate. Then I perform a sample rate change, which increases the sample rate by 10. This is an interpolation with an interpolation factor of 10. My final sample rate will be 1 megahertz, but the noise signal is the same. So the noise signal before was occupying only 100 kilohertz. After the sample rate has changed, but the noise signal is still occupying 100 kilohertz. So that's a way of obtaining a noise signal which is which doesn't occupy the whole spectrum. It only occupies 100 kilohertz or any other thing we want. That's one possibility. Another similar possibility is to generate broadband noise like here, and then use a low pass filter, a band pass filter, any kind of filter to reduce the spectrum range where we have this noise signal. But this approach is more efficient because we are only generating as many noise samples as we need. And here we are generating noise samples to cover all the frequency spectrum with noise, and then we are discarding, not really discarding samples, but averaging samples together. So by doing this, we do less calculations. And we could use this rational resampler. We could even use a low pass filter because it has interpolating option where you can use an interpolation, but I want to use this opportunity to introduce yet another new block, which is called arbitrary resampler. Actually, polyphase arbitrary resampler. Resampler, you can imagine what it means. It means to change the sample rate, so it can perform interpolation, it can perform decimation, can perform any kind of sample rate change. Arbitrary means any, so it can perform any kind of sample rate change. Here, rational resampler was limited to changing by a rational number, by a fraction. And you can see here, this needs to be an integer and this needs to be an integer, so you are limited to a fraction. But here, resampling rate is a real number. You can put here anything, 0.1, 2, 3, 4, 5, 6, whatever. And polyphase is really how the filter for resampling works inside this block. There is a family of techniques in signal processing which are called polyphase techniques, polyphase filters, polyphase approaches. There are even books about polyphase. So it's a whole family of techniques. And in radio astronomy, you might hear sometimes polyphase filter bank or PFB. That's a way of splitting the signal into multiple channels using a polyphase filter. So this uses a polyphase filter for resampling. Things we need to set, just the resampling rate, because the tabs are automatically calculated as happened with the rational resample block. And then the number of filters is the number of filters on the polyphase filter. And unless you are doing something which needs to be really precise or has some very peculiar needs, you can leave the default of 32 and this stop band attenuation. So how to use this? Let's add a GUI entry for the noise bandwidth and then noise bandwidth. Let's make it 150 kilohertz, for example. And here, resampling rate, we are increasing the sample rate because this runs at a low sample rate, or basically 150 kilohertz. And then we need to obtain 1 megahertz, which is the sample rate of everything else. So the resampling rate needs to be greater than 1. Interpolation is always greater than 1. Decimation is always less than 1. And the correct calculation is sample rate divided by what did I call this thing? Noise bandwidth. Another way of looking at this parameter is how many output samples do we produce for each input sample. And that's a good way to remember why interpolation is greater than 1, because we are producing more output samples than we originally had input samples. And decimation is less than 1 because we are basically throwing away samples. So I can make this have 3 inputs, and then if I run this, we can see there's a small mountain here, so this should be 150 kilohertz wide, and yes, more or less, this is 75 kilohertz, so from minus 75 to plus 75, and this is the wideband noise signal we have generated. We can also make a calculation as with the noise, as with the tone. So the power of the 3 signals we have, so the wideband noise, this noise which is limited to 150 kilohertz, and the tone is 1 in all 3 cases. The reason they look different on the spectrum is because of how much power is split in each of the FFT bins. For this, everything is concentrated in a few bins. For this, it is only divided across this region of the spectrum. For this wide one, it is divided over all the spectrum. So that's a way to look at power of this. We can also do CN0 for this thing. So doing CN0 is the same. Let's do this. So noise CN0. Or broadband signal. We can call it however we want. And then the formula. So the formula is the same. We just need to change here. No CN0 broadband. And then rather than noise amplitude, broadband amplitude. And in this way, my noise floor amplitude is fixed. It's set to 1. And then I can play with power. So for example, I can increase this broadband signal by making it 90. Something advantageous of this polyphase arbitrary resampler in comparison also with the rational resampler is that we can change the parameter resampling rate at runtime. So for example, if I want to make this 250, I can just enter 250, and you can notice that let's say the height on the FFT plot changes when I change the bandwidth, and the reason is again because of the power is the same, but then it gets divided over more or less frequency beams depending on how narrow or how wide I make this. And this leads me to something I haven't mentioned yet, which is if you look at the properties, some of these labels have an underline, resampling rate, underline, tabs, underline, and the rest do not have an underline. The reason why there is an underline here is these are parameters that can be changed at runtime while the flow graph is running using this Qt GUI entry or Python code or anything else. And these are fixed. So when the flow graph begins, they have a fixed value until the flow graph finishes. Usually everything which can be easily changed at runtime is possible to change at runtime. Anything which somehow is not really possible cannot be changed. For example, the number of filters. If you wanted to change the number of filters at runtime, you would need to basically throw away your whole filter architecture and do it again from scratch. And in doing so, you would need to try to ensure that there are no glitches in the output signal when you do this change. So that's very difficult to do, and probably no one needs to do it. So that's the reason why number of filters, for example, cannot be changed at runtime, and resampling rate can be changed at runtime. Questions about this? Okay, something else that we already know how to do is placing the signals in different parts of the spectrum, because at the moment this noise signal is at 0 Hertz and this one is at 1 kilohertz. So very quickly, I'm going to add entries for the tone frequency, hertz, floating point, and then, for example, 200 kilohertz, and then tone frequency. And now broadband frequency. Let's make this minus 300 kilohertz, for example. And now there is no frequency parameter in any of these that I can change, but we already know how to move things in frequency. I just need to generate a complex exponential of that particular frequency. So broadband frequency here and multiply. And this is how we can generate anything we want at baseband and then move it to the frequency we really want to have it. So we see now we have the wideband signal here, the narrowband signal there. And using this technique, we could create any number of artificial signals. Broadly speaking, any kind of signal is going to fall within one of these two categories, because either the bandwidth of the signal is so narrow that we might as well say that it has bandwidth 0, and that is this case of the complex exponential or the pure tone, or the bandwidth of the signal might be something that is distinctly larger than 0, and in that case, as long as the signal has a spectrum which is flat, we can generate it in this way. If we want to generate something which doesn't have a flat spectrum, it is also possible to do so. We can use a filter which doesn't have a flat gain, and then basically it shapes the power of the signal across frequency, applies different shape to different frequencies. Okay, something. So the next step is we now know how to generate these signals, and we want to perform spectral analysis. So we want to look at them on the spectrum and say something about them, even detect them, which means say whether they are present or not. And I have already hinted at signal detection when I was playing with this tone CN0 and making it 30. I was saying that now it is almost not visible, and we might want to do a better kind of spectral display for this. So let's do our own. Basically, we're going to do our own version of this GUI frequency sync. To do our own, I want to introduce a new block here, which is quite handy for organizing complicated flow graphs. These are called pad sync and pad source. Sorry, not pad. Pad is for something else. Virtual sync and virtual source. So virtual sync and virtual source. Virtual sync and virtual source form a virtual connection, as their names say, and it basically saves you from running a connection line which might obfuscate the flow graph. So instead of doing that, you place this, you put a unique ID here. So you call this signal, and these two have the same ID, so they are automatically connected. And you could have multiple sources with the same name. So anywhere you need something to be connected to this output, you could have here a virtual source. And that can be handy to organize the flow graph, because if not, then I need to run a connection between these and these, and we would have an ugly line going across all the flow graph. That's the main point of this virtual source and virtual sync. So we want to do an FFT, because the FFT is the way in which we convert from time domain, which all of this is time domain so far, to frequency domain, which is the thing we are looking at in the frequency sync. The FFT has an FFT size. I'm going to use a variable because we are going to be repeating that number several times. And I like to call this NFFT for number of FFT points, and let's make it 4096. NFFT. There is something which is called the window function. Maybe I'll explain today what's an FFT window if there is time. If there is no time, you just need to know that it is a vector. It has the same number of points as the FFT. There are some typical windows that people use commonly, such as Blackman-Harris or Blackman or Hamming or Hanning. So many of those are available as methods on these window objects. So you could use window Hanning, for example, if you want these Hanning windows. So it's going to be some other numbers. This was Blackman-Harris before. And sometimes we do not want to use a window either because of computational use, because using a window needs to perform multiplications by the window. So we might save those multiplications by not using a window, or because the algorithm we are doing requires not to have a window. If you don't want to have a window, you can put an empty list here. So again, this is square bracket, an empty list, and this stands for no window. But let's leave this as Blackman-Harris NFFT, which is a window. You also have windows in NumPy. In case some of the windows you need are not in GNU Radio, you can take those from from NumPy. So, okay. Then there is the shift, which I don't want to get into, and the number of threads, which is how many CPU threads you use to compute FFTs, and this affects performance. So, yeah, those are advanced parameters, so to say. Something I want you to notice is that this is dark blue and this is light blue. And if I try to do a direct connection, this doesn't work. There's an error. And it says source IO size 8 does not match sink IO size 32768. These sizes are in bytes, and this 8 makes sense because we have complex numbers. Each of those, real part and imaginary part, is a 4-byte floating point number, so a float if you do NEC programming. And then what happens with these 32678? What happens is that to do an FFT, you need 4096 samples at a time. The FFT is an operation that operates on vectors. You need a vector of 4096 samples. In contrast to, for example, multiply, in which you multiply one sample at a time. So in GNU Radio, there is the concept of vectors, and some of the blocks have vector inputs and or vector outputs, and you need to match the sizes of the vectors as well. So the reason a direct connection doesn't work is this implicitly has a vector size of 1 because we are not using vectors, and this has a vector size of 4096. So we need something to convert the vector size, which basically means grouping every 4096 consecutive samples into a 4096 entry vector to give it to the FFT. And there is a block to do that, which is called stream to vector, not to be confused with streams to vector, which takes input from multiple streams. So stream to vector. And then this doesn't match, and maybe it's too subtle on the screen, but the color of this is not the same shade of blue as the other two. Basically, the shade of blue is decided by the vector size, so that might give you a clue. What we need is num items NFFT. This vector length, I think it's better explained in the documentation, is the input vector length. And this is the number of items that we put together to form a vector at the output. It can be somewhat confusing, but that's because this block is powerful. It could, for example, take input vectors of size 2 and convert them to output vectors of size 8, for example. But in this case, input vector size is 1. So by doing this, now we get a correct connection. Questions about FFTs and vectors? Okay, the output of the FFT is a vector of complex numbers. Yet again, 4096 complex numbers. But the thing we are displaying on the spectrum is a real variable. It's power. So we need to convert this into power. And basically, the reason this is complex is because in each of the entries of the vector, which is each of the FFT bins, each of the frequency buckets, we have amplitude information, which is the amplitude or the modulus of the complex number. And we have phase information, which is the angle of the complex number. So if we want to take only the amplitude information, there is something called complex to magnitude or complex to magnitude squared. This returns the amplitude of a complex number, and this returns the amplitude squared. This has a square root, if you remember the formula for the absolute value or magnitude of a complex number, and this doesn't have a square root, so it's more efficient. And the thing we want here is power, so it's better to use this rather than using magnitude and then squaring the result. And then many of the blocks we have been using have have a field to operate on vectors. So for example, multiply, you could tell it to multiply vectors of any other size different than 1. So that's what we use here to operate on vectors of length 4096. In this way, we are converting to power. And then at this point, I can already display the output. This is the vector, so there is something called Qt GUI vector sync. We need to tell it the vector size and then not much else. So let's see how this works. I'm going to remove the time sync because I do not really need it. And then we can auto scale, and we see something that doesn't look like the thing below, because it is not in decibels. So these are linear units of power, and you can see that this tone is very powerful, much more powerful than anything else, and it is also jumping a lot. And in here, if we zoom in, we can see this part of the spectrum, but anyhow, this is less convenient to work with and really shows why using decibels is often a good idea. So to convert these to decibels, we basically need to take the logarithm in base 10, and there is a math blocks for that. So logarithm base 10, vector length, NFFT. And there is some n here, and let me check if that's in the documentation. Yes. So the output is n times the logarithm of 10, the input, plus some constant k in case we want to shift things up and down. But here the important thing is the number n. If we are computing decibels of something that is units of power, and here is power because we have magnitude squared, we need n equals 10, because remember 10 logarithm 10. And then if I do this and auto scale again, this looks more or less like the thing below, but it is very jumpy because there is no averaging here. So the thing we are doing at this moment is for every 4096 samples that come in, we compute an FFT, and then we display the FFT. To reduce the noise, we can average several consecutive FFTs, because the signal is going to have the same shape in all of them, but the noise is the thing which is jumping up and down. So by performing averaging, we reduce these noise fluctuations. To average, I'm going to use a new block which is called integrate. I really need to place it before converting to dBs. If you are using dBs, remember that oftentimes you do not want to operate with things which are in dBs. Oftentimes you want to convert those to linear units of power or amplitude or whatever, and perform the operation there and then convert back to dBs. So integrate. Integrate is just a decimation block, and what it does is it sums, for example, if I put here 100, it will sum 100 inputs and produce an output, which is the sum of all those 100 inputs. I also need to tell it to operate on vectors. So as always, 4096. And then I don't get a display here until some time. Hopefully I don't have to wait too much. Yeah, now we get something. So we are averaging 100 FFTs to produce each of the outputs on this plot. Every time that you see the plot changing, the screen refreshing here, is because we have computed 100 FFTs, and then we are displaying the sum of those 100 FFTs. We could divide by 100 to have the average, but it doesn't really matter. It only moves things up and down on this decibel plot. So something we might want to do is 100 is the first number I thought of, but to do this more seriously, we can have a variable and we can set the integration length. And I'm going to call it seconds. So for example, 1 second. That means that every 1 second, my flow graph is going to produce one of these integrations, which is going to be a new spectrum for us to look at in the plot. So integration length seconds. And then I can have a variable here for number integrations. And how much should this be? Well, we have 1 million samples per second, but we are dividing them in vectors of 4096 samples. So this is the number of vectors we have. Sample rate divided by NFFT. Number of vectors per second, or number of FFTs per second. What happens? Somehow this is giving me 0, which looks strange. Anyhow, I clicked OK, and now this is 244, which looks about right. And then we want to round this number because the number of integrations needs to be an integer. So really the integration length will not be exactly 1 second, but something close to 1 second. And then I can set here number integrations. So every second, my flow graph will produce an output. And then there is a trick here, because if we run this, and even on auto scale, we can see that it takes multiple seconds for some output to appear. And this is some peculiarity of how GNU radio works. Eventually something will show up. So there it goes. And when something shows up, we really get a new refresh every second. 1 second, 1 second, 1 second. So what's happening here? This is some peculiarity of GNU radio. What happens is there are buffers. Each of the blocks is only called when there is a certain number of data for it to process. And until then, the data is just accumulating without being processed. So what happens with this is that since we are only producing a 4096 element vector every second, it takes a number of iterations for it to produce enough input so that this block is called to update things on the screen. That's basically what happens. So when you have this situation, this is the usual trick. There is a repeat block, which basically repeats the input. And what I want to do is, okay, we are producing one output every second, but then we are repeating the output 100 times. And the effect of that is flashing the buffers, so the input buffer of this block, and it will make the output appear in 1 second. So that is the trick. Something else we can do with this plot is to set the maximum and minimum values. So I think I'm going to set those at 50 and 90 perhaps. So 90 and 50, there's this Ymax and Ymin. And something else, the x-axis scale, I want that to be in hertz, because it was counting from 0 to 4096. So to make that be in hertz, the start value needs to be sample rate divided by 2. Remember that the minimum frequency we have is minus sample rate divided by 2. And then the step value is, we have computed that before, is how many hertz per FFT bin, and that's sample rate divided by NFFT. So this is how the plot looks like with these two changes. And you can see that now this is in hertz, so it matches the thing we have below. Well, this is megahertz, but you see minus 200, minus 200 kilohertz. We can also auto scale on this one, and maybe I want to set this to median average and maybe try to do a comparison. So if I set the tone to 30, you see that it takes 1 second for the custom plot we have done to update. But when it updates, we can see the tone, and it is clear that this one is better than this one. We might increase the average even more. You can somewhere on the control panel. So on the control panel, you can even add more averaging. But even so, if we make this, I don't know, 27, for example, at some point, it will be clearer to see the tone in here, and in here it will be more difficult to see it. That's because of how the averaging for this plot works in compared to this averaging. The advantage of this averaging is that it's always moving. You can see that the output always changes, and in here we get 1 update per second. So yeah, with this we can simulate signals. We can check how weak of a signal we can detect with a certain FFT size, and I should probably talk about that into some more detail next week, because that is very important for detection of RFI and also for detection of technosignatures and natural radio astronomy sources, to relate the FFT size we have, the integration length we have, with how weak of a signal we can detect in terms of CN0, for example. Any questions about this? This is basically what I have for today.
I have one. Why is the noise floor different on the virtual sync graph than it is on the one below? Like
Yeah, good
something.
Yeah, good question. So this is minus 44 and this is plus 54 or whatever. So it is vastly different. The difference is, so here maybe here there is an FFT. And depending on what convention you use for the FFT, you either do not divide the output, or divide the output by the square root of the number of points, or divide the output by the number of points. So here we are not dividing the output by anything. I don't know about this block. And then here we're integrating, so we are adding 244 outputs. We are summing rather than computing the average. If we were to divide, then logically the output would be smaller. And here probably there is also some other normalization. This all boils down to normalization values. And usually for some reason, engineers like their dB values to be all negative. So somehow this plot has the notion of 0 dBs is maximum something, and then everything is below that, and this one doesn't. But that's the only difference. If we wanted to account for that, that's what the K number here is. This will be added to the values and dBs in the top plot.